Our objective in this lesson is to use properties of the definite integral while applying the fundamental theorem of calculus. So let's recall some of the properties of definite integrals that can help us when evaluating. Going from a to a creates a net area of 0. Reversing the limits of integration makes a negative definite integral. Going from a to b, where c is a value on that interval, can be broken up to say, let's go from a to c, and then add that going from c to b. And if k is a constant, there's a constant multiple of the function that can simply be brought out. And finally, that when we take the definite integral of a sum or difference, we can break it up and do the definite integral of one term plus or minus the definite integral of the other term. A very useful property. Let's also recall that when we're taking the definite integral from negative a to a, or values that are equidistant from 0, and the function is odd, that definite integral will equal 0 because we're creating a net area of 0. What is above the x-axis is the same area as what is below the x-axis. Let's also recall the fundamental theorem of calculus that says that when f is a continuous function on the closed interval from a to b, if capital F is any antiderivative of f on the closed interval a to b, then the definite integral from a to b of f of x dx equals the antiderivative evaluated at b, the upper limit, minus the antiderivative evaluated at a, the lower limit. Let's do some examples that apply these. Evaluate each definite integral using the fundamental theorem of calculus and properties of the definite integral. Integral from 0 to 1 of the square root of x times the quantity x cubed plus 2 dx. Now, when we have a product, we don't have a product rule for taking antiderivatives. So we are going to start by rewriting this integrand in a couple ways. First of all, I don't want a radical, so I'm going to think of this square root of x as x to the 1/2, and then I'm going to distribute the x to the 1/2 so that I do not have a product. So I'll make a note that I'm going to rewrite to not have radicals, because I want exponents if possible, or products. So what will this look like? The integral from 0 to 1 of x to the 1/2 times x cubed, because I'm adding exponents and this 3 is like 6/2, is going to make 6/2 plus 1, or 7/2, plus 2x to the 1/2 dx. Always follows an integral. Integral at the beginning, dx at the end. Now, using our fundamental theorem of calculus, we will take the antiderivative. Using our properties of definite integrals, we will do each one at a time as if they are separate definite integrals. So starting with the first term, x to the 7/2, I add 1 to the exponent. That makes x to the 9/2. Multiply by the reciprocal of the new exponent, 2/9. Plus, add 1 to that exponent, x to the 3/2. Now the 2 is a constant multiple that hangs out while I take the antiderivative, and the rest of the antiderivative is multiplying by the new exponent, so times 2/3. I put my brackets to remind myself that I'm still evaluating this on the interval 0 to 1. Now I could do each of these one at a time. First, I could evaluate this one at 1, evaluate this one at 0, and then subtract the 2. But addition is associative and commutative, so I can really do this in any order that I want, as long as I'm always subtracting what I plug in the lower limit. So first we'll plug in 1. Now actually, I'd rather clean this up a bit, so let's rewrite this antiderivative to be 4/3 x to the 3/2, 0 to 1. Okay, now we'll plug in the upper limit first. So 2/9 times 1 to the 9/2 plus 4/3 times 1 to the 3/2. That was the upper limit plugged in, minus Now I plug in the lower limit, 2/9, 0 to the 9/2, plus 4/3, 0 to the 3/2. This is a proper answer, but I can clean it up, so I might as well. 1 to the 9/2 is just 1, so this is 2/9, plus 1 to the 3/2 is just 1, so plus 4/3, and then all of this over here makes 0. Easy to clean up and much cleaner, but I'm going to go just a little bit further because I can without too much difficulty. Multiplying by 3/3 makes 12/9, and 12/9 plus 2/9, 14/9. Very good. Let's also use the fundamental theorem of calculus and properties of the definite integral to evaluate this definite integral, the integral from 1 to e of the quotient 5x squared minus x plus 4 divided by x cubed. Now, we do not have a product or quotient rules for taking antiderivatives, so first we will rewrite this so that we do not have a quotient. We do not have a quotient rule for antiderivatives. So I'll start by rewriting my integral symbol, and then I'm going to distribute this denominator, 5x squared over x cubed minus x over x cubed plus 4 over x cubed. Now I'm still not ready to take an antiderivative because I still have quotients. Now I just have more of them. So let's continue to rewrite by simplifying. I could write this as 5x to the negative 1, but I remember that that one will not work left like that. So I'm going to rewrite it as 5 times 1 over x minus, this one I'm going to write as, because 1 minus 3 makes negative 2, x to the negative 2 plus 4x to the negative 3. And now I'm ready to take the antiderivative. The 5 hangs out in front while we take the antiderivative of 1 over x, natural log of the absolute value of x, minus, here I add 1 to the exponent for x to the negative 1, and I multiply by the reciprocal of the new exponent, plus, the 4 hangs out in front while I take the antiderivative, add 1 to the exponent makes negative 2, and multiply by the reciprocal of the new exponent. Put my brackets because I have a definite integral, so I will be plugging in values. Before we plug in values, though, this can be cleaned up a lot, and it is much easier to clean it up before we plug in values. So let's proceed with cleaning it up. 5 natural log of absolute value of x. That makes plus, I'd prefer to write it without negative exponents when I have to plug in values, so 1 over x, plus a negative, minus 4 divided by 2 is 2, and x to the negative 2 means it's over x squared, 1 to e. Now I begin by plugging in the upper limit first. 5 natural log of e. I don't have to put absolute values because e is already positive, plus 1 over e minus 2 over e squared. That's all with the upper limit plugged in. Minus, and now the lower limit, 5 natural log of 1 plus 1 over 1 minus 2 over 1 squared. Again, I do have an answer, but I can clean this up a lot, so I'm going to. Remember that natural log of e is 1 and natural log of 1 is 0. So those values are quite easy to compute. 5 times 1 is 5 plus 1 over e minus 2 over e squared. Those are simple enough, left like that. Minus 0 plus 1 minus 2 makes plus 2. Oops, not plus 2, plus 1, because that's 1 and minus 2. So let's fix that, plus 1. And then I might as well combine the like terms to get 6 plus 1 over e minus 2 over e squared. These two are not like terms, and that's as clean as it gets.